let us begin our keynote session number 3. And before the keynote session is about to begin, let me tell something about our honorable keynote speaker 3, Dr. Swagatam Das. Dr. Swagatam Das is the professor and head of Electronics and Communication Science Unit in ISI Kolkata. He is currently serving as an associate professor at the Electronics and Communication Science Unit of ISI Kolkata. With his research interest includes machine learning and non-convex optimization. Dr. Das has published one research monograph, one edited volume, and more than 300 research articles in peer-reviewed journals and international conferences. He is the founding co-editor-in-chief of Farm and Evolutionary Computation International Journal from Elsevier. He has also serving as the associate editor of Pattern Recognition Elsevier IEEE Transaction of on System and IEEE Computational Intelligence Magazine IEEE Access and many such journals. And Dr. Das has 19,000 plus Google Scholar citation and H index of 64 till date. He has acted as an guest editor for special issues in journals like IEEE Transaction on Evolutionary Computational and IEEE Transaction on SNC Part C. He is the recipient of 2012 Young Scientist Young Engineer Award from the Indian National Academy of Engineering INAE. He is sorry for the interruption. He is also the recipient of 2015 Thomas Reuter Research Excellence Indian Citation Award as the highest cited researcher from Indian in engineering and computer science category between 2010 to 2014. We all welcome you, sir, to this event of our conference METASOFT 2022. And today, sir is going to give us the keynote session 3. Thank you, sir.
Thank you very much for the introduction. I hope I am audible to all of you.
Yes, sir, right? You are pretty much audible.
Can you hear me?
Yes, sir, you are pretty much audible.
Yes, sir, you are audible.
Okay. Thank you, and let me express my thanks to Professor Mihir Mohanty, who kindly extended his invitation and also made some provision for shifting this keynote. Actually, I am currently out of state, my own place. I'm in Goa now. For another conference and some academic works, but that's why it has to be shifted. And thanks to Professor Mohanty, he kindly arranged it like this. METASOFT is a very contextual conference of this time because, there is a huge growth. I will be switching off the camera so that we can judiciously use the bandwidth, but later on during the questioning session, I will switch on it. So effectively, meta-heuristics have grown to a very high extent. Sometimes that growth is not very healthy from some certain respects because people continue to come up with new names and try to, sell back the old ideas sometimes, which is not that good. But apart from that, the development in the capability of meta-heuristics have been extended considerably over the last 2 decades or so, and that is really a very interesting development from all sides. And this conference is about how you can use such meta-heuristic algorithms for the software engineering purpose. There are various test pattern generation, testing, evaluation of software systems where we require huge number of meta-heuristic type algorithms because no one knows the exact solution to the problems that emerge. But at the same time, the meta-heuristics must be very carefully before you can deploy these algorithms. You must present them very, very carefully. You must run several acid tests for judging their activity, and only then you get certain that, okay, I am going to use it for a practical purpose. So in this particular talk, I thought it would be better to give you some ideas on how to really present write a paper and present a meta heuristic to the rest of the academic world, how to test it, and how to validate it before you can actually deploy the same for for one particular application. This is something very, very important, and we need to understand that just merely getting some inspiration from any creature around us. In fact, few months before, I had a COVID-19 induced optimization algorithm submitted to one of our journals, which we took no time just to reject. So, so this has become a kind of steady trend, and that's not a very healthy trend, I should better say. Uh, we should actually try to, gather more information and before we can employ an algorithm, and that's a very, very important thing. So evolutionary meta heuristics basically are of three types. Let me share my screen and start the talk. This talk focuses on basically swarm type algorithms, but the things apply to all basically. So let me try to share the whole screen maybe. Can you see my screen? Is it becoming visible gradually? Can one of you tell me whether you can see the slides?
Yes, sir, it is visible.
Okay, fantastic. So what I'm going to do is I'm going to tell you how you should present a new swarm algorithm or a new meta-heuristic algorithm after how many acid tests they should be. You should convince yourself and your reviewers that the algorithm you are going to present is going to work. And in meta-heuristic research community, this is a very standard practice. So basically, I'm going to give you some idea of the benchmarking theory of swarm-based meta-heuristics. I'm going to tell you about certain performance measures for single objective bound constraint optimization problems, and also certain non-parametric statistical test procedures relevant to meta-heuristic research, which is very, very important, and statistical characterization of the parameterized heuristics, and so on. So first of all, we all know about, I hope all of you have heard about particle swarm optimization, or uh, maybe cuckoo search or ant colony optimization type of algorithms. Any such, or even evolutionary computing techniques like genetic algorithms or differential evolution, which are most prominent kind of meta heuristics that we use. I hope you know that a meta heuristic is basically a generalization of these different paradigms known as evolutionary computing, swarm intelligence, then physics based algorithms. So heuristic, this word comes from the Latin word heurisicum, which means to search, and meta means beyond. So a meta heuristic actually integrates multiple thumb rule based methods, and finally, it kind of harmonizes their activities, their functionality, to achieve a bigger goal. What is the bigger goal? To find the global optima of a function, maybe minima, maybe maxima. So to achieve that goal, the first step is to design a representation. That means your problem must be converted into an optimization problem, and the solutions must be, presentable in the form of a vector of certain real numbers sitting together, or maybe in a combinatorial problem, a real number, an integer vector or a binary vector. So, and then there should be, so these vectors, these candidate solutions are the entities which we assume to roam around or to fly through a solution space. They are called particles for particle swarm optimization. They are called chromosomes in genetic algorithms. They are called vectors in differential evolution. They are the cuckoo's eggs in cuckoo search optimization, and so on, so on. So different people have come up with different names, and that's not a healthy process. You should call a trial solution, nothing else. So now, and the basic philosophy is you are going to design next how to perturb the trial solution. Okay, we say we try to see how the position of the search agent, and the search agent is actually personifying a trial solution, should change, and then design. So that is basically the velocity in particle swarm optimization, design of a velocity we adding which the trial solution will actually change. Suitable variation perturbation operators, these are equivalent to, in case of evolutionary computing, we call them reproduction operators. In case of swarm intelligence, we call them variation or perturbation parameters. The things are same. Okay, so we need to change the current set of solutions, and then we need to see whether we have reached a good new set of solutions or we didn't. Apart from that, we must decide how to start the initialization methods. When no information about the problem is at hand, you can go for, uniform initialization from uniform random number. On the other hand, if you have some information of the problem at hand, then you can go for a Gaussian initialization or anything like that. Then you have to decide how to stop. Most often, the common stopping criteria is what? It's like, okay, if my number of function evaluations exceed 5,000, 5 lakh, okay, each time I am evaluating the objective function, not the number of iterations, but the number of function, objective function or fitness evaluations. If that count exceeds certain lakhs, then we will stop. Otherwise, if the best solution of my swarm or my set of solutions has given me a very satisfactory objective function value, which might be, I know the actual optima is at f of x star equal to 0, and I get f of current x best equal to sorry, 10 power minus 5. So I can easily stop there. Okay. And while designing the new algorithms, we must stop, introducing lots of ad hoc and heuristic parameters, because tuning of them is never an easy task. All meta heuristics are essentially simulation driven optimizers. So they are based on the computer-based simulation of some natural event, and they must pass through a series of acid tests. That's just a name. Very tough tests on well-accepted benchmark suits. The primary purpose of this benchmarking is, of course, to identify the strengths and weakness of a particular algorithm. And benchmarking is a process which is meant to help one to choose the right algorithm for his or her practical problem. It's like you are a doctor. You have so many algorithms like the medicines, and an application person comes to you and wants an algorithm which fits best with his or her own problem. So you need to see which algorithm can solve the problem. Even if you do not exactly know the problem, you can get some rough characterizations of the problem, and then you can run your function, your code or your algorithm on a few, benchmark functions which have maximum resemblance with that problem characteristics. That's why during the benchmarking procedure, when we run on certain types of functions, we must make sure they should capture various complex features of the real world problems. This is very, very important. Okay? So the benchmarking theory of evolutionary and swarm and meta heuristics seek response to two main questions. Number one is, given a set of comparative results across various functions, what is the best algorithm? I run 5, 7, 9, algorithms, maybe on 25, 30 functions, and then we want to see what is the best algorithm among all the results. And then how can we map the benchmarking results onto real world situation? Okay? So that is the most important part. to achieve a good algorithm to problem matching. Okay, so we need to see which algorithms are performing especially well on certain properties of an optimization problem. Then we can recommend those particular algorithms when a new problem from real world comes to us exhibiting similar, you know, problem characteristics. So the problem characteristics here are analogous to symptoms of a disease. I'm speaking in a negative sense, but it's this analogy is very right appropriate. So you have it, you come with some certain symptoms, and the doctor matches which medicine works best for these symptoms and then recommends you that medicine only. Same thing happens here. You need to, that's why you need to be a doctor. You need to study well the problem characteristics. Okay, different type. Optimization is an ocean, unfathomable ocean. So many types of problems regularly emerge from all the diverse disciplines of science and technology. Very few of them could be solved in a guaranteed mathematical way. So we need to develop, of course, cheap and automatic process to extract the problem characteristics from a concrete problem instance. These are the usual steps in any benchmarking experiment. Define a problem domain first, whether you are dealing with single objective optimization or multi-objective. Do you have multiple objectives? Are your variables combinatorial? Software test pattern generation works with binary variables or combinatorial variables. Or are they real numbers? Then dynamic, noisy, etc. Given that, first you fix your problem domain. Then you choose n benchmark functions, p performance, let's say n could be 25, 30, something like that. Choose p performance measures. I'm coming to performance measure. Choose k algorithms to compare. Now you run these algorithms on these test functions and evaluate the performance measures. Then you rank the algorithms according to how have they done on each performance measures, and you can find a consensus, analyze the results. After you are confident that, okay, this algorithm is winning maximum number of times, you are going to deploy or select your algorithm. Instead of just using cow, bat, rat, monkey, donkey type algorithms. Nowadays, you have this monkey inspired algorithm, donkey inspired algorithm everywhere. So just for the sake of a new name, you pick up an algorithm and you, without going through all these benchmarking experiments, you run it on a real world problem, gather some results and list them. Maybe you are comparing with 2, 3 obscure algorithms or older methods. Your paper is going to be outright rejected from any good journal. Okay, so be sure of these steps. Now the ranking could be done in two ways. One is the individual ranking, where we just, it should be reflexive and antisymmetric. So if A is better than B, B cannot be better than A, at least on these benchmarks. If A is better than B and B is better than C, then of course A is better than C. Or you can go to a statistical ranking procedure that is called consensus ranking. For example, we can use Borda score or something like that for this purpose. So this is benchmarking theory. Now I was talking about, I don't have enough time to elaborate all the topics, so I will mostly sample some most important things and tell you. You see, the problem characteristics, understanding the characteristics of the problem plays a very big role. And the problem characteristics for, at least for real world single objective optimization problems, understanding the problem characteristics is very, very important. Desirable properties of the benchmark functions are like multimodality, separability and non-separability, scalability, global structure, and so on. So what I have listed here as the bullet points, these are the mathematical properties of the problem that we are going to have. In fact, separability, multimodality, these are also prominent characteristics of any combinatorial optimization problem like traveling salesperson problem or multiple knapsack problem. But real world, real parameter where our decision variables could be continuous variables, for such such real parameter optimization, this is much more contextual. That's why this talk is actually based on real parameters. So what we see is separable problem is a problem which you can decompose it into multiple one-dimensional and easier optimization problems. For example, if your function is simply like this one, sum over xi square minus 10 something, so it's a sum of individual variables following a similar mathematical rule. So you can break it into, d such functions in one variable. That means you have been given a problem x1 square plus x2 square. Instead of solving it together, you can minimize x1 square as a separate function and x2 square as a separate and easier function. Separable problems are very good. They can be solved very easily. Coordinate-wise search you can employ, and they could prove very effective for such functions. For example, uh, the classical differential evolution with best /1/bin type mutation, it's a specific D variant, though those who work with D knows it very well. So with crossover rate of 0.1 serves as one of the best separable optimizer. So this knowledge, this is the insight. If you are applying your algorithm, you are trying to solve a separable problem. If you can see that your problem could be decomposed into one-dimensional functions, easier one-dimensional functions, then you should first try this sort of a D variant with this value of the crossover rate, which is a parameter of D, instead of all those monkey, snake, all those peculiar and very bad algorithms, right? Then, or if you are hell-bent on applying one of these new names because that's a new name, you must show that it is better than this sort of a D through clear experiment. Okay? Otherwise, we are not going to accept that claim. So these are some mathematical intricacies. Usually the functional landscape is visualized in terms of such contour plots. Okay, contours are those lines in the x1, x2, x3 space, or the decision variable space, along which value of the function remains constant. And when you rotate the functional contours through by rotating the variables with it, by multiplying your variable vector, x is the vector of decision variables, if you multiply it with a rotation matrix R, actually you are making your problem non-separable. Okay, so non-separable problems, the total, this entire set of constant cost contours get deformed and rotated. So multimodality, that means inside the domain of definition, you have multiple minima and maxima instead of just a single minima. If your function would have been smooth and single maxima or single minima, we would call it a concave or a convex function, and for them, very nice guaranteed mathematical methods exist. But in case your function is highly multimodal, one example is the famous Weierstrass function, which is continuous everywhere but differentiable nowhere. It's a fractal type function. So if you just sample even a small part of this function, it looks the same. And it's so pointed that you cannot really draw a tangent, just as you cannot draw a tangent to mod of x at x equal to 0. Similarly, so those engineers or those academicians who want to work with optimization techniques, meta-heuristics, they must know the basic mathematics and the nature of functions. These should be the mandatory criteria. Okay, it's not like that it's a very easy thing. So you must know the nature of different types of functions. This is the nature of the function that appears in one of the CEC. CEC is the Congress on Evolutionary Computing Conference, Computation Conference under IEEE. So the CEC 2005 was a very nice test set, benchmark set, and in that test set, this is the 3D visualization of a highly rugged multimodal function. You can see how bad it is. So similarly, ill-conditioned functions. Ill-conditioned functions, you need to check whether the new application problem you are going to solve is ill-conditioned. What does that mean? That means the function is very, very sensitive to one particular variable. If that variable changes, let's say by only 1%, the function may change by 100% or maybe 1000%. If that happens, then the function could not be optimized very easily. It's a very big challenge. For such functions, usually we say if the function is in this quadratic form and A is the matrix containing the coefficients, then the ratio of the singular values of the maximum and minimum singular value of the A matrix is very, very high. So you see, this is a well-behaved function, x1 square plus x2 square. If I make it x1 square plus 10x2 square, or maybe 100 x1 square plus x2 square, I'm giving more emphasis onto one variable, and as a result of that, the constant cost contours, which used to be these circles when we have x1 square plus x2 square, circle has no preference. So it gives equal, importance to both x and y variables. But as you squeeze it into an ellipse, for the ellipse, more change will happen along the major axis. So visualization of this ill-conditioned problem means you are basically looking into such squeezed functional contours, and as a result of that, you are giving more emphasis onto one variable. This is one highly ill-conditioned problem from the CEC benchmark, where you see this pink region is basically the volume. The volume-based search algorithms will end up here, like even differential evolution, even particle swarm optimization, all of them will end up here. They are advanced variants too. Only algorithm which would be very successful and which could drive the solutions in this direction just to reach this optima. This is the optima actually. And the optima have to be followed through a very narrow reach, is the covariance matrix adaptation evolution strategies, or CMAES. CMAES, so if someone claims that I have a good algorithm, let the person test it on this sort of a function and see how close to this reach he can flow. Then there comes the scalability issue. Curse of dimensionality, a term coined by Bellman, and it says if you increase the number of dimensions of your problem, the number of decision variables, then also the search cost increases and the whole search problem becomes very, very difficult because the search volume exponentially triggers up. If you are searching for a single variable function and if you are trying to search between plus 10 and minus 10, the search length is 20. If you are searching along two dimensions, one is along the x-axis and the other one is along the y-axis, then your search area is 20 square. On the other hand, in case of 3 dimensions, search volume is 20 cubed. So think of the situation. If you are searching for, let's say, 500 dimensions, your search volume is 20 to the power 500, which is staggeringly huge. Okay. So in that high dimension, a small population of solution like 40, 100 just looks like sparsely separated points. The search agents or the trial solutions are very much separated from each other and they cannot search that huge volume actually. Then there comes global structure. Global structure means easier function, something like where certain ups and downs are just superposed on an underlying regular geometric structure, like a parabola. So if you see this particular picture, you'll see that the ups and downs are actually very closely related to each other. On the other hand, if your function looks like this function has no global structure. Okay, suddenly there is a very irregular up going region where you will find your maxima. So of course it's a very bad task to try to optimize this particular thing. Then we could have such plateaus. Plateaus are basically the flat regions on the functional landscape. And if you are on the plateau, all your solution points have the same fitness. And as a result of that, the global based, the personal based in PSO, or other guiding particles in PSO or in other algorithms, everywhere there is a special emphasis given to the best member of the population. All of them, all are best. So you don't really have a guideline if your population gets trapped into a flat region. Okay, so you need to understand that. So functions with plateaus, this sort of flat regions, is a special pain in the neck. So there are many benchmark suits. Regularly, the benchmark suits are updated under two competitions. One is hosted by the IEEE CEC, Congress on Evolutionary Computation. These are the uh, different real parameter optimization systems. Under, for example, they can add new nonlinear constraints. They can have linear constraints. They can have dynamic and multimodal scenarios, and so on. And then we could also have, for example, another competition that runs under the another big event in evolutionary computation called GECO, Genetic and Evolutionary Computing Conference. In there, they have this BBOB black box optimization benchmark. All the details are available in different websites for free. Not only details, all the functions and their code. So what is this competition? The organizers post a group of problems taken together and all their codes, how to implement these functions, and they ask for participants to come up with their algorithms and take part in it. If the participants can take part and if they can show that they are doing very good on certain algorithms, they become the winner. So of course, CEC, for example, CEC 2020, 2021, these are the latest competition. Similarly, GECO has updated for different types of problems. In CEC 2011, this is a very popular competition where this was organized by me mainly, and where we actually put this real world optimization problems, each of which could convert into a function optimization scenario. And then we want to, test it. We want to test the algorithm on such real world problems, not only these numerical functions. These numerical functions have been evolved over time. They actually generated from the mathematical programming community or the numerical methods community, actually. So coming to the experiments, I will talk about some, and near the end, we will talk about the statistical testing and other things. So I'm gradually going there. So, but before that, you need to keep all the comparisons fair. The basic rule is use the same computational limit for each competitor. Allow each algorithm the same number of function evaluations, okay? So mostly an abstraction of the computing time for an optimizer or meta-heuristic is how many times it needs to call the function and evaluate the fitness function. So, and sometimes we see that you draw a performance comparison graph, how different algorithms are coming down, are actually reducing the function value. So along y-axis, you plot the logarithmic function value, or logarithm is used to get a nice separation of the different plots. And along the x-axis, what you are plotting is number of iterations. This is a very wrong thing. You must show the time along x-axis in terms of number of function evaluations, because different algorithms can, take different amount of time. If you are comparing a GA with a PSO, with a cuckoo search, with a BAT algorithm or something like that. So all these algorithms are taking different amount of time in their inner loops. Okay. So one iteration of PSO and one iteration of GA are not the same. That's why you should make it more abstract and compare in terms of the number of fitness evaluations, right? And you must also be aware of the hidden labor. What is hidden labor? For example, in heuristic mutation operators, you need to check. They may use distance functions as well. So you need to check, is there any, distance computing? So distance computing, if you need to do, point-to-point distance computing many times, that actually consumes a lot of function evaluations, okay? Performance measures are based on mostly two factors. One is how accurate your solutions are, how near to the optimum point you are reaching. That is the accuracy, and then the speed. Speed means, can you find out an acceptably good solution with least number of fitness evaluations or least amount of computing time? So performance measures must be quantitative, well interpretable, with a meaning relevant in the real world, and simple and easily reproducible. What I said is actually summarized in these very popular performance measures. With Actually, I was little wrong. We also measure another aspect that is called robustness. So three things: accuracy, speed, and robustness. What is robustness? Robustness means all these algorithms include a lot of random numbers. So if you run the same algorithm with all parameters even same on the same function two times, you will get two different answers. If these two answers do not differ by a lot, then we say the algorithm is robust and dependable. Robust means repeated executions of the algorithm will end up with similar results. That's how we measure. The robustness is usually measured by this standard deviation of each run. The standard deviation, if it is very small, so you are going to run your algorithm maybe 25 times on a particular function, every time up to say 3 lakh FEs, same number of FEs, then you are going to average out the final fitness value that you reach at the end of each run, or the best fitness value you got in that run. That's the denoting the best of the run fitness value. And you get this. Then you also compute the standard deviation. If the standard deviation is small enough, that means your algorithm is robust. Okay. Similarly, we have many other such performance criteria. Success rate is basically how many times you are hitting near the optima. If your success rate is higher, that is also an indication of your robustness. So convergence graphs, we are all familiar with this sort of graphs. These are also called run length distribution graphs. Here I'm showing you the a trial convergence graph between different variants of D differential evolution, DE. Along the y-axis, we are plotting the best function value achieved in different at different FEs, and along the x-axis, the number of fitness evaluations or FEs have been plotted. Now, do you notice one thing? All these algorithms are starting from the same initial point. The initial function value is same for all of them. Why? Because for a what should I say, fair comparison, when you are comparing among variants of the same algorithm, your PSO, my PSO, his PSO, her PSO, this way. So you must make sure that all the algorithms are given the same initial population, all of them in each run. So all of them start from the same initial population, such that any difference in their performance could only be attributed to their internal operators, not to chance or luck by which it might have got a very good solution near the optimal point. This we have to keep in mind. And that's it. That is basically what we need for this sort of comparison. And then we can also compare the dimensionality, the resilience to a search space dimensionality. So this graph actually is showing you different types of the performance of different algorithms. And along the x-axis, we are plotting the number of dimensions. Along the y-axis, we are plotting, given the problem is 50 dimensional or 70 or 80 or 100 dimensional, how many FEs are consumed by the algorithm to reduce the function value before a particular below a particular threshold. That is the scalability. Okay. So this is another very, very important thing that you should keep in mind. Statistics should matter the most to a swarm intelligence researcher or to a meta-heuristic researcher. So all of you who want to pursue some research in meta-heuristic algorithms, or especially their applications even to some problems, you should have a basic course of statistics. That's what I can best recommend. And that's because all the algorithms you are handling are stochastic. The results have some element of luck. For scientific papers, if somebody claims my algorithm is better than their algorithm A is better than algorithm B, both are meta-heuristics. So you need to run algorithm A maybe 25 times or 30 times on the particular problem. Algorithm B is also run same number of times. Then you have say two groups, 30 results in one group and 30 results in other group. We say these are two samples from some underlying population. What is population? Population is basically the set of execution of all possible executions of your algorithm on certain problem. And therefore population cannot be, then you have to, for infinitely many times, you need to run your algorithm with different initial populations. For real world, real parameter optimization problems, this is impossible. No one of us has an infinitely time to do this. So what we do is we run the algorithms 25 times or 30 times. That is called a sample of results. Now, statistical hypothesis testing is very, very important. Statistical hypothesis testing actually compares whether the underlying population for these two algorithms are same or not. Try to understand this. You have set of 30 results for algorithm A, 30 results for algorithm B. These are treated as two samples of results from some underlying population. If these two populations are different, then you are on the safe side. That means the two results are really different. We say they are statistically significantly different. But if they are not different, if your hypothesis testing is a way of quantizing this difference, if that difference is not enough, then actually if you claim algorithm A is better than algorithm B, that claim doesn't stand, because your difference between the results of A and B are not statistically significant. But if you can show your results are statistically significant, then you are done actually. So you see, elements of luck. Our PSO just happens to start near the best solution in the benchmark problem we are using, and the other PSO starts far away from the search space from the best solution. And as a result of which, our algorithm is, doing much better. This is a maximization problem actually. So our algorithm is doing much better than their algorithm. Okay? So now the question is our PSO better? So here, for simplicity, I am showing you this x-axis in terms of iterations. So the question is our PSO better? The opposite can also happen. This time, due to a random nature of the SI algorithms, the swarm intelligence algorithms, it could happen that the current-based algorithm outperforms our algorithm because of chance of luck. So in some runs, they could be good. In some runs, we could be good. We need to aggregate many such runs, the results for many such runs, and then we need to run a statistical hypothesis testing. So what we could also do is we could run several replicates of each evolutionary algorithms with different number of seeds, and we could show the average performance of each of the algorithms over time. That is another recipe. But that may not also tell you the full story actually. The average fitness, so it could these are average curves, okay, average performance curves, and it could appear that our evolutionary algorithm is performing much better than the current best algorithm on average. But is that right? That's where you should also plot the 95% confidence interval of each algorithm. This graph shows us that our algorithm does not actually perform better. Our is in blue color, the current best is in green color. This is a toy graph, example graph to make you feel how these things actually matter. So if you plot the 95% confidence interval at each x-axis point, you will see there are gross overlaps between them. And therefore it appeared that actually that algorithms are not that good. So statistical hypothesis testing, hypothesis is a statement which must be, supported with proper evidences. Criminal trial is just an example of a non-statistical hypothesis testing. So in a trial, a jury must decide between two hypotheses. The null hypothesis means which is by default true. So in Indian criminal trial system, the null hypothesis is the defendant is innocent until proven guilty. On the other hand, the alternative hypothesis or the research hypothesis is the defendant is guilty. Now, why this is research hypothesis? You know it very well. The police has to gather a lot of evidences. The police has to do a lot of research to actually substantiate the research hypothesis or the alternative hypothesis. So the jury does not know which hypothesis is true. They must, make a decision on the basis of evidences presented. Same thing happens here also. The in inferential statistics, what we do is our null hypothesis is the two samples. Samples are what? Two set of results. Their underlying populations are same. Their populations are located in the same probabilistic space. On the other hand, that is the null hypothesis. So by default, your algorithm is not beating their algorithm. That is the by default statement. And the research hypothesis or the alternative hypothesis H1 is that algorithms, the underlying populations are different. Population 1 is located on the right or left of population 2. You can assume them as bell-shaped Gaussian curves maybe for now. So which Gaussian curve is on the right? That means whether your algorithm is actually good or bad. These are directional alternative hypotheses. You can be on the right side or left side, greater than or lesser than, this sort of thing. So this is what I was telling you. You have two populations actually, which we can never access because they are the set of all possible executions of your algorithm. So you gather samples from there, and then most of the common statistical hypothesis testing procedures are comparing these means actually. So there are a lot of statistical stuff here which I don't want to discuss in detail. So, but these are available in any good statistics books. Like one such really good book is the Montgomery's book on statistics for engineers. That book is freely available. Montgomery Statistics for Engineers. You can search, download, and then educate yourself. If you are not already doing such tests, and all the tests could be done very simply in MATLAB, or there are a lot of online platforms. There are a lot of different types of tests also. If we want to compare the performance of two algorithms, all we have to do is to check whether algorithms 95% confidence intervals are overlapping. If they don't, then we could make a statement like we are confident that our PSO performs significantly better than the current best known PSO at least 95% of the time. Then there comes hypothesis testing, which you should also do. Every hypothesis testing finally returns you a p-value. This p-value is extremely important. And what does that p-value tells you? It tells you the probability of the null hypothesis to be true. If p-value is very less, let's say 10 power minus 5 or 10 power minus 6 or 10 power minus 3, then we can safely say that we can conclude that the null hypothesis is not true. That means the difference that we notice between our algorithm and their algorithm is real. And therefore, that's why we should cheer that if I say our algorithm is doing good than their algorithm, we are actually making a contribution. Okay? That is where test statistic is some property of the sample which we are going to compare. This could be sample mean or something like that. This is just an example of the one sample Z test. The interpretation, I will skip some of these steps. Now, in case of meta-heuristic, what we do is we use non-parametric hypothesis testing. What does that mean? Parametric tests assume that the underlying population is a Gaussian distributed population or normally distributed population. This assumption itself does not stand if you do not gather too many samples, too many points. If you have too many points with you, then this assumption actually stands because of the central limit theorem. So you need to run, so if you want to do a t-test or an ANOVA test, these are all parametric inference tests. So if you want to do that, you need to run your method 100 times, okay? You have to run it 100 times, at least. So that much time is with nobody. That's why we switch to non-parametric tests, Wilcoxon's rank sum test or Kruskal-Wallis H test, Friedman's FR test. These are all similar type of non-parametric tests where we compare the medians of the two samples, not their means. And Wilcoxon's test is very good. Even if you have run your algorithm 25 times, this test should give you some good inference in terms of the p-values. So the test is simply I'm not going to discuss these mathematical things in details, but you will find them from my slides, and you can email me if you don't understand any particular thing. This is just an example of how we do in this sort of Wilcoxon's test to judge if two variants of D are giving results which are significantly different or not. Okay, usually every test comes with its user-defined alpha level or significance level. So if I specify, okay, my significance level is 0.05, that means if the p-value is less than 0.05, I will accept that the two algorithms are different, because that's enough to conclude that the null hypothesis is rejected. P-value is the probability of the null hypothesis to be true. Okay, but if so that 0.05 must be specified. Standard value is 0.05. It could be 0.01 also. So there are some graphical illustrations on how the populations differ with and how the Wilcoxon's rank sum test actually happens. I'm not going there. So you can see these two very nice tutorials, and one 2020 tutorial which is not included here by our group also. There are beautiful statistical resources. Even in Microsoft Excel, all things you can do. You can do them with these websites where you just simply go and then put your data, put the results of 30 to 40 runs, and it will show you the statistical comparisons. Okay. Now, are the search moves in SI algorithms really different? Not so true. Generally, random walk-based system equations model most of the meta heuristics. You have a current solution at xi. You have a shift of delta x. So you multiply delta x with s. S is your step size, and xi plus s times delta x. That gives you basically the, what should I say, the next step, the next solution actually. And the meta heuristics differ in terms of methods for determining the s and the delta x. That's how they differ. Step size and the direction in which you should move. For D-RAND1 mutation, it's like this. For classical ABC type, ABC is the artificial bee colony algorithm, it's like this. So ABC also performs this and just perturbs one component at a time. So we say ABC prefers more like a local search algorithm. They're just simply penetrating only one. They're just simply perturbing only one component. Where should I shift this thing? So you see, so this is very much equivalent to D-RAND1 bin with CR equal to 1. Similarly, very often the new variants show striking similarity. The G-based guided ABC algorithm is literally a renaming of the D target 2 based one. They called it artificial bee colony. They could not have called it. Similar thing is happening every week almost. A new optimization algorithm is coming up. Some certain groups are promoting this sort of diluted research, and it's not good for science. The perturbation of CS-based Levy flight. Okay, CS is the Cuckoo search algorithm. I think many of you have heard of it. So Cuckoo search with Levy flight. What does it do? It adds a Levy distributed random number scaled by some alpha with the current positions of the solutions and generate a new position. Okay. And that paper came up, I think, in 2010 or so. It has a striking similarity with the Levy evolutionary programming, which was published long back in 2004. Okay, so Levy probability, and this Levy evolutionary programming, LEP, it was published in IEEE Transactions on Evolutionary Computation. So you see, this is also a kind of repackaging of old things in new names, and this is very, very wrong. So just for the sake of a new name, don't take an algorithm. Take an algorithm when you see it is really doing good on the established benchmarks, it is really able to defeat or outperform the CEC or Gecko competition winners, then only you should use that. More points of similarity are here, like chemotaxis of BFO is a variant of the stochastic hill climbing approach and so on. Chicken swarm optimization, for example, it came in, I think, in 2014. This sort of coefficients, this is very, very similar. First of all, the equation is very similar to PSO. Those who know PSO would realize that. And then these S1 and S2 are adapted in this way. This is exactly similar to PSO with adaptive acceleration coefficients. Okay. Cat swarm optimization. I don't know how cats can swarm because they always quarrel with each other. So this is simply a global only PSO model. In fact, this Joya algorithm. How many of you have heard of Joya algorithm? Jaya victory. Have you heard of the Jaya algorithm? So now you try to find what Jaya algorithm does. That is not included in my slides actually. What Jaya algorithm does is they, get their solutions are attracted towards the best members of the population, the best solution, and their solutions are repelled from the worst members of the solution. Okay, so this idea was proposed, I think, very recently, 2013-14, sometime like that. And long before that, since 2004-5, we have the attractive repulsive particle swarm optimization, which does exactly the same thing. The particles are attracted towards best solution and repelled from worst solutions. It's a very simple, thinking on which multiple papers do exist. And then in 2010s, some researchers are claiming it to be a novel one, new algorithm, naming it Jaya. And this is a very, very, once again, a very poor trend. We must be very, very cautious about this trend. Okay. Okay, so if you, this was a very limited test. If you see the test, the Bonferroni done test, which is a statistical test showing you how much these new algorithms like GSO, Group Search Optimizer, ABC, Cuckoo Search, Firefly, how much they differ in gross performance over the CC benchmarks from classical methods like comprehensive learning PSO or differential evolution with global neighborhood. We see that DEGL or CLPSO, these are from two traditional families. Now, if you ask me what are the well-accepted traditional families of meta-heuristics, in fact, all the new researchers should start with those families. The first is evolutionary programming and evolution strategies. They are almost same, ESEP, in which we have CMAES. Then, of course, genetic algorithms. Genetic algorithms are by default the discrete optimizers or combinatorial optimizers, very good at software testing like problems. Then I can recommend particle swarm optimization, differential evolution, and ant colony optimization. So how many did I name? I named 5 algorithmic families: ES and EP, then genetic algorithms, particle swarm optimization, differential evolution, and ant colony optimization for combinatorial problems. Out of these 5 algorithmic families, most of these so-called novel algorithms are just repackaging the same. I'm telling in a very gentle way actually. They are just repackaging the old stuff in new names in their desperate attempt to become a pioneer, to increase their number of citations, and finally to publish a paper. This is a very, 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 very wrong tendency, and we should all be aware of that. So, and when you write a new paper, you should, involving meta-heuristics, this is from one of our surveys, you should always decode or decipher the language that you are going to use. And these languages sometimes carry too much of, analogies, or too much of, kind of different types of names which could simply coming from certain metaphors. So you need to put your ideas in a metaphor-free language. You see this table. In this table, we are showing how we should do that. Bees, mating, and marriage. This is an algorithm, honeybees mating optimization algorithm. Somebody wrote this algorithm, and then they came up with queen and drone, broods, workers. Why these terms should be used in an algorithm literature, in an optimization paper? What are queen and drone? They are the candidate solutions. Broods, newly generated candidate solutions. Workers, local search heuristics for improving offspring solutions. So these are the actual language of optimization. So do not call a trial solution a bee, a cuckoo's egg, intelligent water drop, particle Call it a trial solution or candidate solution. Be straight, write in metaphor-free language. If you really want to contribute and publish in a high degree venue, like IEEE Transactions on Evolutionary Computation or Swarm and Evolutionary Computation, then you must come up with a metaphor-free direct language. Okay, this is very important. So looking into the future, so many algorithms, so little time. Inspirations for designing the optimizer are coming from diverse sources, ranging from human society to flu virus. So does everyone wants to be a pioneer? Are these numerous algorithms really effective? Will they survive in the long run, or their influence will remain mostly stipulated, confined within the world of paper writing? Then they are of no use actually. Do we really need yet another ABC or PSO, or do we really need yet another new algorithm? Or do we require specialized algorithms for solving problem-specific research, solving certain particular problems, solving a particular problem class, like the ill-conditioned problems. So this is very, very important. For example, in this particular paper, what we did, this doesn't propose any new algorithm. This paper actually analyzed the characteristics of a very much real-world problem, which is protein structure prediction. So when the proteins fold into tertiary and secondary structures, what that structure will be? Can we predict that from the amino acid chains inside the protein? That thing we are looking at. Okay. So this is what we are going to do. Basically, just give me one moment. Just one moment.
Thank you so much, Swagatam sir, for the nice presentation.
Just wait.
Uh, any, anybody having any questions?
Sir is, sir is waiting. Sir is telling. Sir, I should
No,
show
yeah, yeah.
something.
Sorry, I actually got a call. That's why I just have, will take one
Okay.
more minute.
But till now, it's not.
So
Okay,
I got a call actually. That's why I had to leave.
okay sir. Continue, sir.
So judging the functional characteristics from end-to-end measurement, you take a particular problem, let's say software test pattern generation problem, or let's say some problem related to software engineering. You study that problem very well, simply convey the characteristics of the problem and how they match with the existing meta heuristics. That could actually lead to a beautiful paper, okay, which everyone will be benefited and everyone will refer. Okay. Similarly, we need to, that's why, and that's where the benchmarking thing is coming. Can we look into the similarity between benchmarks and real world problems? Like you can see here, these are benchmark functions, 6-hump camelback function, for example. That has a striking similarity with the Cogging torque design problem from power engineering. Similarly, 2D inverted Schubert function has a very good similarity, this landscape, with the frequency modulated sound wave synthesis and so on. So you see, if you study these characteristics, then if your algorithm works much better on this sort of benchmarks, then you can say, well, they are going to work on this sort of real world problems as well. This is very important. So with this much, I would like to stop here. And now as you were telling, if you have any question, I would be very happy to respond back actually. Okay.
Anyone is having any questions?
So if you have any question, we can discuss that, or even if you wish to write to me about something, or you need some reference to some literature or book, you can write to me. I will be happy to revert back. And that's it.
Thank you, sir, for such a nice keynote session. We are obliged, and if any of us is having any kinds of doubt or any kind of further inquiry about this session, we will be definitely be connecting to you. I think Mihir sir
Thank
wants to
you.
say
Thank you.
something.
Thank
ମୋ
you for
ପାଖରେ
your
ରହିବ
quality also.
ସବୁ
Uh,
ଜାଗାରେ ମୋ ପାଖରେ ରହିବ
hope the conference goes fine.
ସବୁ ଜାଗାରେ ମୋ ପାଖରେ ତ ବର ପାଖରେ ଅଲଗା
Yes, sir. Thank you.
ମୋ ପାଖରେ
Thank you.
Mihir sir,
Thank you.
Mihir sir,
See
do
you
you
also
want to
on.
say
yes
something?
thank you very much
Sir,
you have
kindly share the
content
PPT.
you have content
PPT to
at
me,
least
sir.
your valuable time I am very happy
Yes.
I am waiting for that only
Sure, sure,
so
sure.
okay
Thank you. Bye bye.
thank you
Sir, kindly share your PPT.